Welcome to the final third of the course. In the first section, you reviewed the basic building blocks of the Internet. And in the second section, you learned how networks deal with large amounts of network traffic. In the final section, you'll learn how network operators manage their networks. More importantly, these topics will introduce you to the forefront of networking research.
That's right. We're going to cover software-defined networking, traffic engineering, and network security.
Let's get started.
Welcome to the third course in CS6250, where we will be discussing network operations and management. This segment in the course has 3 lessons. The first lesson is focused on software-defined networking and its role in making network operations and management easier. The second module covers traffic engineering, which is the process by which network operators reconfigure the network to balance traffic demands across the network. The third lesson covers network security. We will start with a lesson on software-defined networking, but before we jump into the details, I'd like to motivate a little bit why. In particular, I plan to tell you about the role of network operators in running the network. So what is network management? Network management is the process of configuring the network to achieve a variety of tasks. Network configuration achieves a variety of tasks, including balancing traffic load across the network, achieving various security goals, and satisfying business relationships that may exist between the network that's being configured and neighboring networks, such as the network's upstream internet service provider. A key aspect to network management is configuring the network. Unfortunately, if the network is not configured correctly, many things can go wrong. Configuration mistakes can lead to problems such as persistent oscillation, whereby routers can't agree on a route to a destination, loops, where packets get stuck in between 2 or more routers and never actually make it to the destination, partitions, whereby the network is split into 2 or more segments that are not connected, and black holes, where packets reach a router that does not know what to do with the packet and drops it, as opposed to sending it on to its ultimate destination. Let's start with a brief overview of software-defined networking, or SDN. We'll first start by defining SDN. In particular, we'll talk about what is a software-defined network. Then we'll talk about what are the advantages of SDN over a conventional network architecture. We'll overview the history of SDN, the infrastructure that supports it, in particular how SDNs are designed and built, and the applications of SDN, specifically what they can be used for and how they can be used to simplify various network management tasks. Perhaps the best way to understand what an SDN is to compare it to the behavior of today's networks. Today's networks have 2 functions. The first is the data plane, whose task it is to forward packets to their ultimate destination. But in order for the data plane to work, we also need a way of computing the state that each of these routers has that allows the routers to make the right decision in forwarding traffic to the destination. The state that lives in each of these routers that allows the routers to make these decisions about how to forward packets are called routing tables. It's the job of the network's control plane to compute these routing tables. In conventional networks, the control and data plane both run on the routers that are distributed across the network. In an SDN, the control plane runs in a logically centralized controller. Additionally, the controller typically controls multiple routers across the network, and often the control program exerts control over all of the routers in the network, thus facilitating network-wide control. These 2 characteristics are the defining features of a software-defined network. The separation of data and control allows a network operator to build a network with commodity devices where the control resides in a separate control program. This refactoring allows us to move from a network where devices are vertically integrated, making it very tough to innovate, to a network where the devices have open interfaces that can be controlled by software, thus allowing for much more rapid innovation. Let's survey a brief history of SDN. Previous to 2004, configuration was distributed, leading to buggy and unpredictable behavior. Around 2004, we had the idea to control the network from a logically centralized high-level program. That logically centralized controller focused on the Border Gateway Protocol and was called the Routing Control Platform, or RCP. In 2005, researchers generalized the notion of the RCP for different planes. The decision plane, which computed the forwarding state for devices in the network, the data plane, which forwarded traffic based on decisions made by the decision plane, and the dissemination and discovery planes, which provide the decision plane the information that it needs to compute the forwarding state, which ultimately gets pushed to the data plane. Around 2008, these concepts effectively hit the mainstream through a protocol called OpenFlow. OpenFlow's intellectual roots are with the RCP and 4D, but OpenFlow was made practical when merchant silicon vendors opened their APIs so that switch chipsets could be controlled from software. So suddenly there was an emergence of cheap switches that were built based on open chipsets that could be controlled from software. This development effectively allowed us to decouple the control plane and the data plane in commodity switching hardware. SDN has many advantages over conventional networks. It's easier to coordinate behavior among a network of devices. The behavior of the network is easier to evolve, and it's also easier to reason about. These characteristics are all rooted in the fact that the control plane is separate from the data plane. Having a separate control plane or control program allows us to apply conventional CS techniques to old networking problems. So whereas before it was incredibly difficult to reason about or debug a network's behavior, if the network behavior is now controlled by a logically centralized control program, we can use techniques from programming languages or software engineering to help us reason about the behavior of the network. As far as SDN's infrastructure is concerned, the control plane is typically a software program written in a high-level language, such as Python or C. On the other hand, the data plane is typically programmable hardware that's controlled by the control plane. The controller affects the forwarding state that's in the switch using control commands. OpenFlow is one standard that defines a set of control commands by which a controller can control the behavior of one or more switches. SDN has many applications, including data centers, wide area backbone networks, enterprise networks, Internet Exchange Points, or IXPs, and home networks. Later modules in this course will explore how software-defined networks can solve network management problems in some of these areas. In this course, we will focus in particular on the first three applications. So as a quick quiz, which of the following are examples of control plane operations? Computing a forwarding path that satisfies some high-level policy, such as an access control policy, computing a shortest path routing tree, rate limiting traffic so that the overall sending rate doesn't exceed a certain throughput, load balancing traffic based on a hash of the packet source IP address, or authenticating a user's device based on its MAC address. Please check all options that apply. The job of the control plane is to compute state that ultimately ends up in the data plane. So computing a forwarding path that satisfies a high-level policy is something that the control plane would do. The control plane can also compute shortest path routing trees, and it might make decisions about whether or not a user's device should be allowed to send traffic or not based on that device's MAC address. Rate limiting is something that is typically done in the data plane, and the load balancing example that we have listed here is such that a router or a switch would make decisions in the data plane based on a hash of the source IP address. So all of the decisions are being made at forwarding time, not by a centralized high-level program. Let's quickly review the difference between the control plane and the data plane. The control plane is the logic that controls forwarding behavior. Examples of control plane functions include routing protocols, as well as logic for configuring network middleboxes. Now, a routing protocol might compute shortest paths over a topology, but ultimately the results of such computations must be installed in switches that actually do the forwarding. The forwarding table entries themselves, and specifically the actions associated with forwarding traffic, according to the control plane logic, is what constitutes the data plane. So examples of data plane function include forwarding packets at the IP layer and doing things like switching at layer 2. So to reiterate, routing protocol functions that compute the paths are control plane functions, whereas the act of actually taking a packet on an input port and forwarding it to an output port is a data plane function. So why is separating the data and control planes a good idea? The first reason is independent evolution and development. Thus, software control of the network can evolve independently of the network hardware. The second reason that separating data and control planes is a good idea is the opportunity to control the network behavior from a high-level software program. Controlling the network from a high-level program, in theory, allows network operators to debug and check network behavior more easily than in the status quo, where network behavior is determined by the distributed low-level configuration across hundreds of switches and routers. The separation of data and control provides opportunities for better network management in data centers by facilitating such network tasks as virtual machine migration to adapt to fluctuating network demands. In routing, the separation of data and control provides more control over decision logic. In enterprise networks, SDN provides the ability to write security applications, such as applications that manage network access control. In research networks, the separation of data and control effectively allows us to virtualize the network so that research networks and experimental protocols can coexist with production networks on the same underlying network hardware. So as a quiz, what are some of the reasons for separating the control and data planes? Eliminating a single point of failure, ability to scale to much larger networks, independent evolution of the data and control plane, separating vendor hardware from control logic, or ease of reasoning about network behavior. Please check all options that apply. Separating the data and control plane can allow for independent evolution of the data and control plane, separating vendor hardware from the logic that controls the behavior of the network, and the potential to more easily reason about network behavior since the behavior is now controlled from a single logically centralized control program. While it's possible that separating the control plane from the data plane could result in architectures that are more fault-tolerant or more scalable, the separation of data and control plane does not inherently make the network more fault-tolerant or more scalable. Therefore, neither of the first two options apply. One example where SDN can provide huge wins is in the data center. A data center typically consists of many racks of servers, and any particular cluster might have as many as 20,000 servers. Assuming that each one of these servers can run about 200 virtual machines, that's 400,000 virtual machines in a cluster. A significant problem is provisioning or migrating these virtual machines in response to varying traffic loads. SDN solves this problem by programming the switch state from a central database. So supposing I have two virtual machines within the data center that need to communicate with one another. The forwarding state in the switches in the data center ensures that traffic is forwarded correctly. If we need to provision additional virtual machines or migrate a virtual machine from one server to another in the data center, the state in these switches must be updated. Updating the state in this fashion is much easier to do from a central controller or a central database. Facilitating this type of virtual machine migration in a data center is one of the early killer apps of software-defined networking. This type of migration is also made easier by the fact that these servers are addressed with layer 2 addressing, and the entire data center looks like a flat layer 2 topology. What this means is that a server can be migrated from one portion of the data center to another without requiring the virtual machine to obtain new addresses. All that needs to happen for forwarding to work is the state of these switches needs to be updated. The task of updating switch state in this fashion is very easy to do when the control and data planes are separate. Let's have another quiz on data centers. So how does the control data plane separation make managing data centers easier? The ability to monitor and control routes from a central point of control, the ability to migrate virtual machines without renumbering host addresses, a requirement for fewer switches, or making load balance automatic. Please again check all that apply. So as we discussed, control data plane separation can make it easier to manage the data center by monitoring and controlling routes from a central point and allowing virtual machines to be migrated without renumbering host addresses. The control data plane separation does not inherently make it possible to build a data center with fewer switches, nor does it automatically balance load. As another example where control and data plane separation comes in handy, let's look at the security of internet backbones, where filtering attack traffic is a regular network management task. Suppose that an attacker is sending lots of traffic towards a victim. In this case, a measurement system might detect the attack, identify the entry point, and a controller such as the RCP might install what is called a null route to ensure that no more traffic reaches the victim from the attacker. Two fundamental challenges with SDN are scalability and consistency. In an SDN, a single control element might be responsible for many forwarding elements. So a control element might be responsible for hundreds to thousands of switches. Of course, for redundancy and reliability, typically we want to replicate the controller. So while the controller is logically centralized, physically there may be many replicas. And in such a deployment scenario, we need to ensure that different controller replicas see the same view of the network so that they make consistent decisions when they're installing state in the data plane. A final challenge that's also worth mentioning is security or robustness. In particular, we want to make sure that the network continues to function correctly in the event that a controller replica fails or is compromised. So as a brief quiz or thought question, let's think about some approaches for coping with the scalability associated with the control and data plane separation. One could, for example, eliminate redundant data structures in the controller, or only perform control operations for a limited number of network operations, such as only performing control operations for routing decisions. One might send all traffic through the controller to minimize forwarding decisions that routers and switches need to make. One could cache forwarding decisions in the switches, or run multiple controllers. Eliminating redundant data structures can help save memory in the control program running at the controller. Only performing a fixed number of network management operations, such as routing, can ensure that the controller doesn't have to do too much, thereby improving scalability. Caching forwarding decisions that the control plane has already made in the switches can ensure that not too much traffic is redirected to the controller, and running multiple controllers can distribute the load of the control plane across multiple replicas. Sending all traffic to the controller only increases the controller load and would not help with scalability. Now that we have a better understanding of the benefits of separating the data and control plane, let's now have a look at the many different options for SDN controllers. There are a number of different SDN controllers that exist, including Nox, Ryu, Floodlight, Pyretic, Frenetic, Procera, Routeflow, Trema, and the list goes on. In this lesson, we will explore the merits of these three controllers, and when we get to the lessons on programming SDN, we will take a close look at Frenetic and Pyretic. Let's now jump in and take a look at these three controllers. Nox was a first-generation OpenFlow controller. It is open source, stable, and widely used. There are two flavors of Nox, Classic Nox and the new Nox. Classic Nox was written in C++ and Python and is no longer supported. The new Nox is C++ only. The codebase is fast, clean, and well supported. More information about Nox is available at noxrepo.org. In a Nox network, there may be a set of switches and various network-attached servers. The controller maintains a network view, and the controller may also run several applications that operate on that network view. The basic abstraction that Nox supports is a switch control abstraction, where OpenFlow is the prevailing protocol. Control is defined at the granularity of flows, which are defined by a 10-tuple in the original OpenFlow specification. So depending on whether a particular packet matches a subset of values specified as a flow rule, the controller may make different decisions for packets that belong to different parts of flow space, or packets that match different subsets of the fields defined by a flow. A flow is defined by the header, or the 10-tuple, which I just alluded to, a counter, which maintains statistics, and actions that should be performed on packets that match this particular flow definition. Actions might include forwarding the packet, dropping it, or sending it to the controller. When a switch receives a packet, it updates its counters for counting packets that belong to that flow and applies the corresponding actions for that flow, which might include forwarding, dropping, or sending to a controller. The basic programmatic interface for the Nox controller is based on events. A controller knows how to process different types of events, such as a switch, join, or leave, a packet in or a packet received event should the switch redirect the packet to the controller, as well as various statistics. The controller also keeps track of a network view, which includes a view of the underlying network topology, and it also speaks a control protocol to the switches in the network. That control protocol effectively allows the controller to update the state in the network switches. The Nox controller implements the OpenFlow protocol. Nox is implemented in C++, and it supports OpenFlow 1.0. A fork of Nox called CPQD supports versions 1.1, 1.2, and 1.3. The programming model is event-based, and a programmer can write an application by writing event handlers for the Nox controller. Nox provides good performance, but requires you to understand and be comfortable with the facilities and semantics of low-level OpenFlow commands. Later in this module, we will explore controllers based on Pyretic and Frenetic that do not have this characteristic. Nox also requires the programmer to write the control application in C++, which can be slow for development and debugging. To address the shortcomings that are associated with development in C++, POX was developed. POX is widely used, maintained, and supported. It's also easy to use and easy to read and write the control programs. Of course, as might come with implementing a controller in Python, the performance of POX is not as good as the performance of Nox. So as a quick quiz, when might you use POX? In a class project, in a large internet data center, or in a university research project? Please check all that apply. You might use POX in a class project or in a university research project where there's a need to quickly prototype and evaluate a brand new control application. POX is less applicable in a large internet data center because it does not perform as well as other controllers. Other controllers include Ryu, which is an open source Python controller. Ryu supports OpenFlow 1.0, 1.2, and 1.3, as well as the Nicira extensions. It also works with OpenStack. The support for the later versions of OpenFlow and the integration with OpenStack are advantages over other SDN controllers. Because Ryu is implemented in Python, it still does not perform as well as other SDN controllers such as Nox. Another popular SDN controller is Floodlight. Floodlight is written in Java. It supports OpenFlow 1.0 and is a fork from the early Beacon controller. Floodlight is maintained by Big Switch Networks. Advantages include good documentation, integration with the REST API, and good performance. Unfortunately, it also has a fairly steep learning curve. So you should use Floodlight if you already know Java, if you need production-level performance and support, and you will use the REST API to interact with the controller. So we can compare these two controllers with the two controllers that we already discussed, Knox and Pox. We have controllers in 3 different languages, Python, Java, and C++. We have controllers that support later versions of OpenFlow and support OpenStack. And we have controllers that provide better performance, as well as controllers that are easier to use for rapid prototyping. All of these controllers are still relatively hard to use because they entail interacting directly with OpenFlow flow table modifications, which operate at a very low level of matching on flows and performing specific actions. As we'll see, it's possible to develop programming languages on top of these controllers that make it much easier for a network operator to reason about network behavior. Before we jump into higher level programming languages, however, let's first see how we can use these existing control frameworks to customize network control. In this lesson, we will learn how to write control programs to customize network control. We will review the operation of a hub and a learning switch. Then we will explore how to use the Pox controller to create a simple mininet topology. And then we will explore how to customize the Pox controller to perform 2 types of network control. As a review, when a host sends a packet to a hub, the hub maintains no state about which output port a packet should be forwarded to reach a particular destination. Therefore, the hub simply forwards the input packet on every output port. In Pox, this code is fairly simple. When the controller starts, it adds a listener that listens for a connection up, which is a connection from a switch. When the switch connects, it simply sends an OpenFlow flow modification back to the switch that says flood all packets out every output port. The first function here in bold creates the OpenFlow message, and the second sends that message back to the switch. In contrast, a learning switch maintains a switch table that's initially empty, but when a packet arrives on input port 1, the switch creates a table that associates host A with output port 1, such that whenever a subsequent packet is destined for destination A, the switch knows to forward the packet via output port 1. I won't show you the full Python code here, but it's fairly simple, and you can go look at the Pox distribution to see the learning switch example. As before, when the first packet arrives at the switch, it is diverted to the controller. At this point, the controller maintains a hash table that maps the address to the output port. When it sees that first packet from host A, it updates the address and port table. If the packet's a multicast packet, the controller makes a decision to flood that packet on all output ports. Likewise, if there's no table entry for the destination for that packet, the controller also instructs the switch to forward the packet on all output ports. If the source and destination address are the same, the controller instructs the switch to drop the packet. Otherwise, the controller installs the flow table entry corresponding to that destination address and output port. Installing that flow table entry in the switch prevents future packets for that flow from being redirected to the controller. Rather, all subsequent packets on that flow can be handled directly by the switch, since it now knows which output port to send a packet for that particular destination. OpenFlow makes modifying forwarding behavior easy because forwarding decisions are based on matches on the OpenFlow 10-tuple. Layer 2 switching is simply a match on the destination MAC address which has the corresponding action of forwarding out a particular output port. If all of the fields are specified for forwarding out a particular output port, then we have flow switching behavior. If all of the flow specifications are wildcarded except for, say, the source MAC address to make a forwarding or drop decision, then we have a firewall. Constructing a firewall is as simple as building a hash table that stores key value pairs, where the table maps a switch and source MAC address to a true or false value depending on whether traffic should be forwarded or dropped. The controller might then only decide to forward traffic if the firewall entry maps to true. It is important to emphasize the performance implications of caching the decisions at the switch. So packets only reach the controller if there's no flow table entry at the switch. If, on the other hand, there is a flow table entry at the switch, then the switch can simply forward the packets rather than sending them to the controller. So when a controller decides to take an action on a packet, it installs that action as a flow table entry in the switch, and that decision or flow table entry is cached until that flow table entry expires. In summary, customizing control is easy. We've explored how to use the POX controller to develop alternate control programs, and it's possible to turn a switch into a firewall in less than 40 lines of Python code. We also explored the performance benefits of caching rules and decisions to avoid sending too much traffic to the controller. As we know, forwarding performance in the switches is fast, but whenever we have to send traffic to the controller, it slows things down. So whatever decisions we can cache in the switch will only serve to improve the performance of the network.
Now that you know that network management is a tough, complicated process, we're going to take a look at one of the most recent advancements in networking, software-defined networking.
Along the way, you're going to complete two exciting projects in Mininet. In the first, you will write your own virtual switch. In the second, you'll use a programming language designed for software-defined networking to create a firewall.
In this lesson, we'll be exploring consistent updates in SDNs. As a reminder, from last lesson, we looked at how to update switch flow table entries using OpenFlow control commands from the controller. The OpenFlow API, however, does not provide specific guarantees about the level of consistency that packets along an end-to-end path can experience. So, for example, updates to multiple switches along a path in a network that occur at different times may result in problems such as forwarding loops. Additionally, if updates to the switches along an end-to-end path occur in the middle of a flow, packets from the same flow may be subjected to two different network states. These two problems are known as consistency problems. The first problem is known as a packet-level consistency problem, and the second problem is known as a flow-level consistency problem. In this lesson, we will explore these problems in more detail and look at various approaches to guaranteeing consistent updates in SDNs. To think about consistency properly, we first need a notion of a high-level programming model that sits on top of what we would call the southbound interface. We'll talk about how to write applications that use the controller interface that we learned about in the last lesson that can rely on a better notion of consistency than existing controller platforms currently provide. Let's first think about how we want to program these applications and what type of abstraction the applications would require from the underlying control interface. Let's consider a network of SDN switches, such as OpenFlow switches, and a controller that is controlling those switches. And let's assume that we would like to write a program using this interface. We can think about this programming as proceeding in three steps. The first is that the controller needs to read or monitor network state as well as various events that may be occurring in the network. These events may include failures, topology changes, security events, and so forth. The second step is to compute the policy based on the state that the controller sees from the network. This is effectively what we talked about last time as the role of the decision plane in deciding what the forwarding behavior of the network should be in response to various states that it reads from the network switches. The third step is to write policy back to the switches by installing the appropriate flow table state into the switches. Consistency problems can arise in two steps. First, the controller may read state from the network switches at different times, resulting in an inconsistent view of the network-wide state. And second, the controller may be writing policy as traffic is actively flowing through the network, which can disrupt packets along an end-to-end path, or packets that should be treated consistently because they are part of the same flow. Both reading and writing network state can be challenging because OpenFlow rules are simple match action predicates, so it can be very difficult to express complex logic with these rules. If we want to read state that requires multiple rules, expressing a policy that allows us to read such a state can be complicated without more sophisticated predicates. For example, let's suppose that when we are reading state, we'd like to see all web server traffic except for source 1234. Simple match action rules do not allow us to express such exceptions. As a solution to this problem, we need a language primitive that allows us to express predicates. Here is a simple statement that has several predicates, such as and not. A runtime system can then translate these predicates into low-level OpenFlow rules, ensuring that they are installed atomically and in the right order. Another problem that arises is that switches only have limited space for rules. It's simply not possible to install all possible rule patterns for every set of flows that we'd like to monitor. For example, if we'd like to count the number of bytes for every source IP address and generate a histogram with the resulting traffic, we would potentially need a flow table entry for every possible source IP address. It's simply not possible to install all of these possible rules. The solution is to have the runtime system dynamically unfold rules as traffic arrives. A programmer would specify something like a group by source IP address, and the runtime system would dynamically add OpenFlow rules to the switch as traffic arrives, thereby guaranteeing that there are only rules in the switch that correspond to active traffic. Another problem that arises when reading state is that extra unexpected events may introduce inconsistencies. A common programming idiom is that the first packet goes to the controller, and once the controller figures out what policy to apply for that flow, the controller then installs rules in the switches in the network corresponding to that flow. What if more packets should arrive at the switch before the controller has a chance to install rules for that flow? At this point, multiple packets may reach the controller, but the application that is running on top of the controller may not need or want to see these additional packets. So the solution is to have the programmer specify via a high-level language a limit of 1, indicating that the application should only see the first packet of the flow, and that the subsequent packets should be suppressed. The runtime system then hides the extra events. So to remind you where we are, we talked about problems with consistency when reading state from the network, and we talked about 3 approaches to helping guarantee consistency when reading state: predicates, rule unfolding, and suppression. And let's now talk about primitives that can help maintain consistency when writing state. There are many reasons that a controller might want to write policy to change the state in the network switches, including maintenance, unexpected failure, and traffic engineering. Any of these network tasks involve or require updating state in the network switches. And when that state transition happens, we want to make sure that forwarding remains correct and consistent. In particular, we would like to maintain the following invariants. There shouldn't be any forwarding loops, and there shouldn't be any black holes whereby a router or switch receives a packet and doesn't know what to do with it. There also shouldn't be cases where traffic is going where it shouldn't be allowed to go because of the network being in an inconsistent state. Let's now consider an example of what might happen when policies are written to the network if they're written in an inconsistent fashion. Let's consider a case where we have a network that is performing shortest path routing to some destination, and the link weights are as I've shown here in the figure. Traffic in the network would flow along the paths shown in green. Let's suppose now that an operator wants to change the network state to shift traffic off of this link. He could do so by updating the link weight. In doing so, the new shortest path from this top router would be as follows. But what if the state in the top switch occurred before the state in the bottom switch could be updated? In this case, we would have a potential forwarding loop. Traffic would proceed to the bottom switch, but the bottom switch would still have the old network state and would continue to forward traffic to the top switch, resulting in a forwarding loop. If rules are installed along a path out of order, packets may reach a switch before the new rules do. So in this type of model, we would have to think about all possible packet and event orderings to ensure that consistent behavior resulted. So we need atomic updates of the entire configuration. The solution to this problem is to use a two-phase commit so that packets are either subjected to the old configuration on all switches or to the new configuration on all switches. But packets aren't subjected to the new policy on some switches and the old policy on others. The idea is to tag the packet on ingress so that the switches maintain copies of both P1 and P2 for some time. When all switches have received rules corresponding to the new policy, then incoming packets can be tagged with P2. After some time, when we're sure that no more packets with P1 are being forwarded through the network, we can only then remove the rules corresponding to policy P1. Now, the naive version of two-phase commit requires doing this on all switches at once, which essentially doubles the rule space requirements, since we have to store the rules for both P1 and P2. We can limit the scope of the two-phase commit by only applying this mechanism on switches that involve the affected portions of the traffic or the affected portions of the topology. So as a quick quiz, what types of problems can arise from inconsistent applications of writing policy? Inability to respond to failures, forwarding loops, a flood of traffic at the controller, or security policy violations. Inconsistent writes can result in forwarding loops or security policy violations where traffic ends up going to parts of the network where it shouldn't go as a result of inconsistent switch state. The ability to respond to failures is orthogonal to consistency. A flood of traffic at the controller technically involves problems with reading state in a consistent fashion, but since there also involves a step where the controller writes state to the switches while packets are still arriving at the controller, I would consider that answer to be correct as well. What are some approaches to coping with inconsistency? Running different controllers for different switches, keeping a hot spare replica that has a complete view of the network state, keeping the old and new state on the routers and switches, and switching over only when all of the switches have received the new state, or relying on the routers themselves to resolve the conflict. In this case, there's only one correct answer, which is keeping the old and new state on the routers and switches. This is the two-phase commit approach that we talked about. Running different controllers for different switches could obviously result in inconsistent state, since each of those controllers may be making independent decisions. Keeping a hot spare replica does no good if the replica also writes state inconsistently to the network, and resolving conflicts on the routers also doesn't work because no router has a complete view of the network state. Let's now talk about an application of software-defined networking, which is network virtualization. So we'll talk first about what network virtualization is, then we'll talk about how it's implemented, and then we'll talk about some examples and applications, such as Mininet. So network virtualization is simply an abstraction of the physical network, where multiple logical networks can be run on the same underlying shared physical substrate. For example, a logical network might map a particular network topology onto the underlying physical topology. And there might be multiple logical networks that map onto the same physical topology, and these logical networks might actually share nodes and links in the underlying physical topology. But each logical network has its own view, as if it were running its own private version of the network. Now you can see from this picture that the nodes in the physical network need to be shared or sliced. So the nodes in the physical topology might be virtual machines. Similarly, a single link in the logical topology might map to multiple links in the physical topology. The mechanism to achieve these virtual links is typically through tunneling. So a packet that's destined from A to B in the logical topology might be encapsulated in a packet that's destined for node X first, before the packet is decapsulated and ultimately sent to B. It may also be easy to understand virtual networking as an analogy to virtual machines, which you may be familiar with already. So in a virtual machine environment, we have virtual machines where a hypervisor arbitrates access to the underlying physical resources, providing to each virtual machine the illusion that it's operating on its own dedicated version of the hardware. Similarly, with virtual networking, a network hypervisor of sorts arbitrates access to the underlying physical network to multiple virtual networks, providing the illusion that each virtual network actually has its own dedicated physical network. One of the main motivations for the rise of virtual networking was the ossification of the Internet architecture. In particular, because the Internet protocol was so pervasive, it made it very difficult to make fundamental changes to the way the underlying Internet architecture operated. There was a lot of work on overlay networks in the 2000s, but one-size-fits-all network architectures were very difficult to deploy. So rather than trying to replace existing network architectures, network virtualization was intended to allow for easier evolution. In other words, network virtualization enables evolution because we didn't have to pick a winner for a replacement for IP. We could instead let multiple architectures exist in parallel. Now, this was sort of a greenfield view of why virtual networking was potentially a good idea. In practice, network virtualization has really taken off in multi-tenant data centers, where there may be multiple tenants or applications running on a shared cluster of servers. Well-known examples of this include Amazon's EC2, Rackspace, and things like Google App Engine. Large service providers such as Google, Yahoo, and so forth also use network virtualization to adjust the resources that are devoted to any particular service at a given time. So what are some of the motivations for network virtualization or virtual networks that we've discussed? Easier troubleshooting, facilitating research and evolution by allowing coexistence of production networks with experimental ones, better forwarding performance, and adjusting the resources of the network as demands change. Please check all that apply. As we discussed, virtual networks can facilitate research and evolution by allowing experimental networks to coexist with production networks. Because the networks are virtual, they can be scaled up and down, adjusting the resources that are devoted to any one particular service as demands change. We discussed this in the context of production networks such as Google and Yahoo. Virtual networks are not inherently easier to troubleshoot, nor do they necessarily provide better forwarding performance. In fact, forwarding performance may be worse due to the additional level of indirection that has been added. Some of the promised benefits of network virtualization are more rapid innovation, since innovation can proceed at the rate at which software evolves, rather than on hardware development cycles, allowing for new forms of network control, and potentially simplifying programming. It's important to make a distinction between network virtualization and software-defined networking. Network virtualization is arguably one of the first killer applications for SDN, and in some sense, SDN is a tool for implementing network virtualization. But the two are not one and the same. Remember, the defining tenet of SDN is the separation of the data and control planes, whereas the defining tenet of network virtualization is to separate the underlying physical network from the logical networks that lie on top of it. So SDN can be used to simplify many aspects of network virtualization, but it does not inherently abstract the details of the underlying physical network. So which of the following are characteristics of network virtualization, but not necessarily characteristics of SDN? Be careful. The distinction between SDN and virtual networks was as we discussed in the previous part of this lesson. Allowing multiple tenants, to share underlying physical infrastructure, controlling behavior from a logically centralized controller, separating logical and physical networks, or separating data and control planes. Again, please feel free to check all that apply. Network virtualization can allow multiple tenants to share the underlying physical infrastructure, and it also separates logical and physical networks. The other two options are defining characteristics of software-defined networking, but not of network virtualization. So virtual networks have various design goals. They should be flexible, able to support different topologies, routing and forwarding architectures, and independent configurations. They should be manageable. In other words, they should separate the policy that a network operator is trying to specify from the mechanisms of how those policies are implemented. They should be scalable, maximizing the number of coexisting virtual networks. They should be secure by isolating the different logical networks from one another. They should be programmable, and they should be heterogeneous in the sense that they should support different technologies. So virtual networks have two components, nodes and edges. The physical nodes themselves must be virtualized. One possible way of virtualizing a node is a virtual machine. A more lightweight way of virtualizing a node is using a virtual environment, such as a vServer or a jail. The hypervisor, or whatever technology is enabling the virtual environment, can effectively slice the underlying physical hardware to provide the illusion of multiple guest nodes, or multiple virtual nodes. Examples of node virtualization include virtual machine environments such as Xen or VMware, or what's called OS-level virtualization, or virtual environments, such as Linux vServers. Now, in a virtual network, we need to connect these virtual machines. Each virtual machine or virtual environment has its own view of the network stack, and we may want to provide the appearance that these nodes are connected to one another over a layer 2 topology, even if they are in fact separated by multiple IP hops. One possible way of doing that is to encapsulate the Ethernet packet as it leaves the VM on the left in an IP packet. The IP packet can then be destined for the IP address of the machine on the right, and when the packet arrives at this machine, the host can decapsulate the packet and pass the original Ethernet packet to the VM or the virtual environment that's residing on that physical node. Each one of these physical hosts may in fact host multiple virtual machines or virtual environments, which creates the need for a virtual switch that resides on the physical host. This virtual switch provides the function of networking virtual machines together over a virtual layer 2 topology. The Linux bridge is an example of a software switch that can perform this type of function. Open vSwitch is another example of software that performs this type of glue function. You can see more information about Open vSwitch on the URL provided here. The Mininet tool that we've been using in the course is actually an example of network virtualization. We are in fact running an entire virtual network on your laptop. When you start Mininet using the MN script, each host in the virtual network is a bash process with its own network namespace. A network namespace is kind of like a virtual machine, except it's a lot more lightweight. It's in fact called OS-level virtualization. So each one of these virtual nodes has its own view of the network stack, as shown here with these interfaces, but it has a shared file system, and it's not in fact running its own independent virtual machine. The root namespace manages the communication between these distinct virtual nodes, as well as the switch that connects these nodes in the topology that you set up. Virtual Ethernet pairs are assigned to namespaces. For example, S1 ETH1 is assigned to an interface in H2's network namespace, and S1 ETH2 is assigned to a network namespace in H3's virtual network namespace. The OpenFlow switch effectively performs forwarding between the interfaces in the root namespace, but because the interfaces are paired, we get the illusion of sending traffic between H2 and H3. When we make modifications to the OpenFlow switch via the controller, we're in fact doing that in the root namespace. In summary, virtual networks facilitate flexible, agile deployment by enabling rapid innovation at the pace of software, vendor independence, and scale. We talked about the distinction between SDNs and virtual networks, as well as various technologies that enable virtual networks, such as virtual machines for creating virtual nodes and tunneling for creating virtual links. In this lesson, we'll talk about the why and how of programming SDNs. Unfortunately, programming OpenFlow is not easy. It offers only a very low level of abstraction in the form of match action rules. The controller only sees events that switches don't know how to handle. And there can be race conditions if switch level rules are not installed properly, as we've already seen in the lesson on consistent updates. The solution to this is to provide some kind of northbound API, which is a programming interface that allows applications and other kinds of orchestration systems to program the network. So where we have at the low level the controller updating state in the switch using OpenFlow flow modification rules, we may have applications or orchestration systems that need to perform more sophisticated tasks, such as path computation, loop avoidance, and so forth. But we need a higher level programming interface that allows these applications to talk to the controller, so the application isn't writing low-level OpenFlow rules, but rather is expressing what it wants to have happen in terms of higher-level behaviors, without regard to such things as whether or not the rules are being installed in a consistent and correct fashion. Various people may write these applications, including network operators, service providers, researchers, and really anyone who wants to develop capabilities on top of OpenFlow. The benefits of such a northbound API are vendor independence, as well as the ability to quickly modify or customize control through various popular programming languages. The idea is that these applications might be written in high-level programming languages such as Python and wouldn't actually have to perform low-level switch modifications, but rather could express policies in terms of much higher level of abstractions. Examples of such applications include the implementation of a large virtual switch abstraction, security applications, and services that may need to integrate traffic processing with middle boxes. This programmatic interface is called the Northbound API, and currently there's no standard for the Northbound API, as there is for the Southbound API in OpenFlow. But we'll look at various APIs in programming languages that each compile to OpenFlow rules that are installed on switches across the network. One example of a programming language that sits on top of such a northbound API is Frenetic, which is a SQL-like query language. For example, Frenetic would allow a programmer to count the number of bytes grouped by destination MAC address and report the updates to these counters every 60 seconds. The group by statement allows a grouping of counts by the destination MAC address. Where allows restriction to only count traffic coming from a web server coming in on a particular port, and every specifies that the results of this query should only be returned every 60 seconds. More information about Frenetic is available at freneticlang.org, and in the course we'll actually be using a language called Pyretic that is based on the same underlying theory as Frenetic, except that it's embedded in Python. One issue with programming at this higher level of abstraction is that an operator might write multiple modules, each of which affects the same traffic. For example, an operator might write an application that monitors traffic, another one that specifies how routing should take place, another that involves the specification of firewall rules, and yet another that balances traffic load across the links in the network. Ultimately, all of these applications or modules must be combined into a single set of OpenFlow rules that together achieve the network operator's overall goal. For this, we need composition operators, or ways that specify how these individual modules should be combined or composed into a single coherent application. Let's now talk about two different ways to compose policies. One way of composing policies is to perform both operations simultaneously. For example, one might want to forward traffic, but also count how much traffic is being forwarded. Both of those operations can be performed in parallel. Another way of composing policies is in sequence. Sequential composition performs one operation, then the next. For example, We might want to implement a firewall, and whatever traffic makes it through the firewall might then be subjected to the switching policy. One example of sequential composition might be a load balancer. In this example, a policy might take some traffic coming from half of the source IP addresses and rewrite that to one server replica, and take the other half of the traffic and rewrite it to the other replica. After the load balancer rewrites the destination IP address, we need a routing module to forward the traffic out the appropriate port on the switch. In this case, we've used sequential composition to first apply a load balance policy that rewrites the destination IP address based on the source IP address where the traffic is coming from, and sequentially apply a routing policy that forwards the traffic out the appropriate port depending on the resulting destination IP address after that rewrite has taken place. Notice that we can use predicates to specify which traffic traverses which modules. Those predicates can apply specific actions based on things like the input port and the packet header fields. The ability to compose policies in this fashion allows each module to partially specify functionality without having to write the policy for the entire network. This leaves some flexibility so that one module can implement a small bit of the network function, leaving some functions for other modules. This also allows for module reuse, since a module need not be tied to a particular network setting. For example, in this particular example where we've applied a load balancer followed by routing, the load balancer spreads traffic across the replicas without regard to the underlying network paths that traffic takes once those destination IP addresses are rewritten. In summary, we've covered two concepts. One is the notion of a northbound API, which sits on top of an SDN controller and provides and exposes higher-level abstractions that allows the operator or programmer to write policies without regard to how OpenFlow rules eventually get installed. We've also talked about two different composition operators, parallel composition and sequential composition, which specify how individual simpler policies can be composed to implement more complex network applications, thus allowing different SDN control programs to independently perform tasks on the same traffic. In this lesson, we will look at Pyretic, which is an SDN language and runtime that implements some of the composition operators that we discussed in the last lesson. The language is a way of expressing these high-level policies, and the runtime provides the function of compiling these policies to the OpenFlow rules that eventually are installed on the switches. One key abstraction in Pyretic is the notion of located packets, the idea that we can apply a policy based on a packet and its location in the network, such as the switch at which that packet is located, or the port on which that packet arrives. Pyretic offers several features. The first is the ability to take as input a packet and then return packets at different locations in the network. This effectively allows the implementation of network policy as a function that simply takes packets and returns other packets at different locations. The second feature of Pyretic is the notion of Boolean predicates. Unlike OpenFlow rules, which do not permit the expression of simple conjunctions such as and or negations like not, Pyretic allows the expression of policies in terms of these predicates. Pyretic also provides the notion of virtual packet header fields, which allows the programmer to refer to packet locations and also to tag packets so that specific functions can be applied at different portions of the program. Pyretic also provides composition operators, such as parallel and sequential composition, which we discussed in the last lesson. The notion of network policy as a function contrasts with the OpenFlow style of programming. In OpenFlow, policies are simply bit patterns, in other words, match statements, for which matching packets are subject to a particular action. These types of policies can be particularly difficult to reason about. In contrast, in Pyretic, policies are functions that map packets to other packets. Some example functions in Pyretic include the identity function, which returns the original packet, none or drop, which returns the empty set, match, which returns the identity if the field f matches the value v and returns none or drop otherwise, mod, which returns the same packet with the field f set to v, forward, which is simply syntactic sugar on mod, to say that the output port field in the packet should be modified to the parameter specified, and flood, which returns one packet for each port on the network spanning tree. In OpenFlow, packets either match on a rule or they simply fall through to the next rule. So or, not, etc. can be tough to reason about. In contrast, Pyretic's match function outputs either the packet or nothing, depending on whether the predicate is satisfied. For example, we could apply a match statement that says match destination IP equals 10.0.0.3, and this function would take packets as input and only return packets that satisfy this particular predicate. In addition to the standard packet header fields, Pyretic offers the notion of virtual packet header fields, which is a unified way of representing packet metadata. In Pyretic, the packet is nothing more than a dictionary that maps a field name, such as the destination IP address, to a value. Now, these field names could correspond to fields in an actual packet header, but they can also be virtual. For example, we could provide a match statement based on a switch, indicating that we only want to return packets that are located at a particular switch, or on the input port, indicating that we only want to see packets whose attributes match a particular input port. The match function matches on this packet metadata, and the mod function can modify this metadata. Pyretic enables the notion of both sequential and parallel composition, as we've discussed in previous lessons. For example, we could match all packets for a particular destination IP address and send them or forward them out a particular output port. The double greater than sign shown here is the way of expressing sequential composition in Pyretic. Parallel composition allows two policies to be applied in parallel. In this example, we match on a particular destination IP address and subsequently forward the traffic out output port 1. In parallel, we apply a different set of policies that match on a different source IP address and output the packets on a different output port. In Pyretic, the plus operator performs parallel composition of policies. Pyretic allows an operator to construct queries that allow the program to see packet streams. For example, the packets query allows the operator to see packets arriving at a particular switch with a particular source MAC address. The one parameter here indicates that we only want to see the first packet that arrives with a unique source MAC address and switch. We can then register callbacks for these packet streams that are invoked to handle each new packet that arrives for that query. Dynamic policies are policies whose forwarding behavior can change. They are represented as a time series of static policies. The current value of the policy at any time is self.policy. A common programming idiom in Pyretic is to set a default policy and then register a callback that updates that policy. In the assignment, you'll create a similar topology that you created in the POX assignment, but we'll now use Pyretic to implement a simple switch and firewall. In Pyretic, every first packet with a new source MAC address at the switch is read by a query. The policy is updated with a new predicate every time a new mapping between a MAC address and an output port is learned. In the assignment, you'll also create a dynamic firewall policy, register a callback to check the rules, and sequentially compose your firewall policy with a learning switch that's provided as part of the Pyretic distribution. In summary, Pyretic allows operators to write complex network policies as functions. It allows an operator to express predicates on packets, including things such as and, or, and not. It provides the capability to specify and modify virtual packet headers as packet metadata, and it provides ways to compose complex network policies from simpler independent ones. As a quiz, which of the following is the appropriate Pyretic rule for sending traffic from source IP address 10.0.0.1 to destination IP address 10.1.2.3 and traffic from source IP address 10.0.0.2 to destination IP address 10.2.3.4. The following policy matches the appropriate source IP addresses and forwards to the corresponding output destination IP address. Each of these matching and forwarding operations can happen in parallel.